Hello there, Mr. Sutton bringing you the AB Calculus 4-9 homework solutions on linearization. For number 1, we're given the graph of a function, and they want to know which of the following has the greatest value. So we've got f of a, that's the y value down here. Now we're not sure what the exact value is. All we can really say at this point is that that is less than 0, negative. So hopefully we know something about the other answer choices that will allow us to say that it's bigger than this value. All right, so now choice B, f prime of a. Again, we don't know what the exact number is. This is the instantaneous rate of change at a. We know it's a slope. We know that it's pretty positive. It's greater than 0. Beyond that, we don't know much else. So let's keep going. Choice C, f prime of c, up here, well, the slope up here is going to be 0 or pretty close to it. So that's definitely going to be less than the slope at a. So this choice B is still the winner. D, f of d minus f of c, so that's the change from c to d. This is going to be negative. You're taking a smaller y value, subtracting a bigger one. So that's less than 0. So choice B is still the winner. Let's check out choice E now, and this is where things get a little interesting. This is saying the average rate of change between points A and B. So if you were to draw a tangent line, or not even a tangent line, just a secant line from A to B here, the slope of that line. Again, we don't know what that value is, but we do know it's positive. So it's down to the instantaneous rate of change at A and the average rate of change from A to B. Which of these is a larger number? The key on this one is to recognize that this is a concave down function. That means we know the slope is decreasing as we move along this function. So that this slope here at point A, this is going to be greater than any of the slopes, instantaneous rates of change that you meet along the way. And for that reason, it's also going to be bigger than any average between this and any of the other slopes along the way. So because this is concave down, because the slope is only going down, the average rate of change from A to B has to be less than the instantaneous rate of change at A. So that means that choice B then is the best answer on this. For number 2, we have a twice differentiable function that's concave up on the interval 0 to 2, and we have a tangent line of 3x minus 2 at x equals 1 for this function. Which statement has to be true about the derivative of f? So here's a rough, intuitive kind of visual of this. We've got some concave up function, and we have a tangent line that has a positive slope, so it has to be on this side of our concave up function. We don't really know what's going on back here or over here, but it's roughly going to look like this. Let's get a little more rigorous, though. What do we know based on the information they gave us? Since we have a concave up function, we know that f prime, the slope of this function, has to be increasing between 0 and 2. We don't know what the slope is at 0 or 2. It might be negative, it might be positive, but it's increasing the whole way. Next, since we have a tangent line at 3x minus 2, we know the slope of the original function at x equals 1 has to be the slope of that tangent line, namely 3. So we know f prime of 1 is going to be exactly 3, no matter what else is true. Well, this tells us a little bit more. Since our function is increasing from 0 to 2, and it's exactly 3 at x equals 1, we know between 0 and 1, the f prime must be less than or equal to 3. And we know that, again, since it's increasing, after we get to 1, between 1 and 2 at least, f prime has to be greater than or equal to 3. So in light of all this, let's take a look at our answer choices. First answer choice, f prime of x less than or equal to 3 on 0.9 to 1. Well, that's in line with what we were saying here, which is before we get to 1, our slope has to be less than or equal to that tangent line slope of 3. And intuitively, you can see this has to be true on this sketch here. Let's look at the other answer choices, though, just to be sure. So choice B, f prime greater than or equal to 3 on 0.9 to 1. Well, no, that's exactly the opposite of what we said here. Choice C, f prime's less than 0 on the interval from 0.9 to 1.1. It could be negative to the left of 1, since it's less than 3, but certainly after we get to the x value 1, we have to have positive slopes, positive f primes. So choice C can be eliminated pretty quickly. Choice D is a little bit tougher. F prime is greater than 0 on the interval from 0.9 to 1.1. But again, we don't know how much less than 3 our slope is until we actually, get to that x value of 1. We know it has to be less than 3 on the interval x equals 0 to x equals 1. We don't know how much less than 3. It might be negative for all we know. So choice D, we can't pick that one either. Choice E, f prime is constant on the interval. Well, no, this is a concave up function. We always have f prime increasing. It can't be constant that whole way. So choice A is our best answer then. For number 3, we have this function, e to the x over 3. We want to know which of the following is the tangent line equation for the point 3ln4, comma 4. So for tangent line equation, we need an x, a y value, and a slope. They gave us the x and the y value. We just need the slope when we plug our x value into the derivative of this function. So the derivative of f, that's going to be e to the x over 3 times the tail of 1/3 for that inner function. So let's actually plug 3ln of 4 into this. So if I do that, I've got 3ln of 4 over 3 in the exponent. 3's are going to cancel. That's just e to the ln of 4, which is just 4, because the e and the ln cancel out. So altogether, you have 4/3 for the slope. So I'm going to plug these things into point slope formula. We could use the tangent line L of x kind of formula, but if you look at all the answer choices, they're all in this format, so we might as well go with this. So we're again going to have then y minus the y value 4 equals slope of 4/3 times x minus the x value 3ln of 4. And looking at our answer choices, it looks like there's only one answer choice that has that, choice A. For number 4, we want to know for small values of h, the function 4th root of 16 plus h is best approximated by which? Looking at the answer choices, these are all linear expressions. So I'm going to try to come up then with a linear approximation kind of formula to represent this. I'm going to start by writing my L of x formula. L of x equals f of a plus f prime of a times x minus a. But now I have to figure out my a value, and I can't use x. I need to use h because this is a function of h. For the a value, the key on this is they said it's for small values of h. Well, that means we must be pretty close to 0, right? Because that would be like as h approaches 0. So then let's use an a value of 0 to give us those small h values. So I'll rewrite this L of x formula as L of h equals f of 0 plus f prime of 0 times x minus 0. All right, let's find all of these different things in here. Really just need f of 0 and f prime of 0. F prime of h, well, f of h is 16 plus h to the 1/4 power. So the derivative of that would be 1/4 times 16 plus h to the negative 3/4 power if we use the power rule. And we have an inner function of 1 for this 16 plus h, so we don't have to worry about that. Let's go ahead now and plug in 0 for h, because that's our a value. So f prime of 0, 16 plus 0 is 16. The negative 3/4 power of that, well, that's going to be 1 over the 4th root of 16 to the 3rd power. So that's really 1 over 2 to the 3rd, or 1 over 8. 1/4 times 1 over 8 comes out to 1 over 32. Now we need f of 0. That's going to be just the 4th root of 16 plus 0, which is the 4th root of 16, which is 2. Plugging this in, we've got f of 0, so 2 plus 1 over 32 times h minus 0, which we can just simplify to 2 plus h over 32. So that's going to give us choice B. For number 5, f is a twice differentiable function with values for f of 2, f prime of 2, f double prime of 2 that we'll look at in a minute. What's the value of the approximation of f of 1.9 using a tangent line at x equals 2? So we're going to start with my tangent line formula. L of x equals f of a plus f prime of a times x minus a. In this case, we have an a value of 2. So we have f of 2 plus f prime of 2 times x minus 2. And we actually know all of this stuff. They gave us all this information. They also gave us f double prime of 2, which turns out to not matter at all for this problem. It was just kind of false or information we didn't need. So we've got f of 2, which is 1, plus f prime of 2, which is 4, parentheses x minus 2. And what we actually need is to know the approximation at 1.9. This was a no calculator question, so we have to do our best without the calculator. Let's plug in 1.9 for x and hope things aren't too nasty. So 1.9 minus 2, that's going to be negative 0.1. So this is going to be 4 times negative 0.1, which is really just negative 0.4. So we've got 1 minus 0.4, which we should hopefully be able to do without a calculator. That is 0.6, which gives us answer choice B. For number 6, f is a differentiable function such that f of 0 is negative 5 and f prime of x is less than or equal to 3 for all x, of the following which cannot be a value for f of 2. The key on this one is realizing that we can't go up by more than 3 for every step we take to the right. The maximum instantaneous slope is 3. So since we can't increase by more than 3 for each step to the right, let's just see what the upper bound is if we add 3 for a couple steps to the right. How many steps do we need? Well, the first x value we know stuff about is 0, and we want to know the y value when x is 2. So let's calculate f of 1. F of 1 has to be less than or equal to the negative 5 that we're starting with at f of 0, plus the maximum possible slope of 3. So that's just going to be negative 2 as an upper bound. And then f of 2 is going to be that upper bound plus the maximum possible slope of 3 again. So f of 2 can't be any bigger than 1. Looking at our answer choices, all of the answer choices except for 2 over here, choice E, are less than or equal to 1. So since 2 is too big, we're going to pick choice E. For number 7, f of x is a twice differentiable function, and let's let y equals t of x be the tangent line to the graph of f at x equals 2. If that tangent line has a greater or equal value to the actual function for all x values, which of the following must be true? So what we're basically saying here is the tangent line needs to be above the curve, not under. The tangent line's y value has to always be greater than or equal to the curve. Well, if the tangent line is above the curve, that means that your curve must be concave down. It must be one of these frowny faces, right? If the function's concave down, that means that f double prime must be negative. And the only answer choice that says that is choice E. For this problem, we're given some differentiable function f whose derivative is x over y, and we're told that f of 8 is 2. Based off of this, we want f of 8.1's approximation using a tangent line from x equals 8. So for this, we'll start with our tangent line approximation formula. That's L of x equals f of a plus f prime of a times x minus a. And specifically, since a is 8 in this problem, that's our launching off point for our tangent line, we can write this as f of 8 plus f prime of 8 times x minus 8. And 8.1 is what we ultimately want to plug in for our x value, so hey, let's put that in there as well. Okay, so we need to figure out what f prime of 8 is. We actually already know f of 8. They gave it to us in the problem. For f prime, though, we're going to have to use this x over y formula. So in order to use this, I need to plug in 8 for my x value, and 2 is the y value that goes with that. So we have 8 over 2, which comes out to 4. So plugging all that back in and simplifying a little bit, I can write all of this stuff equals f of 8 we said is 2 plus 4 times, well, this is going to come out to 0.1. This was a no calculator question, so you needed to be able to do this arithmetic here. This is 2 plus 0.4, which is 2.4. Choice C. On this problem, f is a function that's differentiable for all real numbers, and the table above gives us values of f and its derivative at selected points between negative and positive 1.5. And they're also telling us, and this will be important for this problem, the second derivative is positive on this interval here. All right, so part B, they want us to write an equation of the line tangent to f at the point where x equals 1. use it to approximate f of 1.2, and then tell us if the approximation is greater than or less than the actual value of f of 1.2. So there's actually three different parts to this problem. Let's find that tangent line first. So I'm going to start with L of x equals f of a plus f prime of a times x minus a. This is my standard tangent line formula here. And now I'm going to plug in some different pieces. F of a in this case, we're talking about f of 1. A is 1. That's the launching off point for our tangent line. So f of 1, they told us in the table, that's going to be negative 4. F prime of 1 is going to be 5. They also gave us that. So we can write negative 4 plus 5 times x minus 1. Again, a was 1 on this one. So there is the equation of our tangent line. We've done the first part of the problem. Now we need to use this to approximate f of 1.2. So basically just plug 1.2 in for x. And if you leave it like this, you've actually done what you were supposed to. This is numerically equivalent to whatever approximation they were looking for. Having said that, if you wanted to simplify it, we could. So this is going to be 5 times 0.2, which is going to be 1. So we have negative 4 plus 1, which comes out to negative 3. All right, next part of the question. Is this approximation, is negative 3 greater than or less than the actual value of f of 1.2? So in order to figure this out, we need to know the concavity of the curve on the interval that we're doing this tangent line approximation. Specifically, we need to know, is our curve concave up or concave down on the interval between a, which is 1, and x, which is 1.2. Looking back up here, they said the second derivative was greater than 0 between negative 1.5 and positive 1.5. What that means, since it's positive on this whole interval here, and it's actually positive on the closed interval, but all we needed it on was the open interval, that tells us that our function f is concave up on the interval in question, on 1 to 1.2. And you have to spell out that you're concave up on the interval between a and x in order to get credit on this. What that means, since the tangent line is going to be on the bottom of the curve, if our curve is a smiley face, is concave up, that means that the value we just found with that tangent line, negative 3, must be less than the true value of f of 1.2. For part C of this problem, we want to find a positive real number r having the property that there exists a c between 0 and 0.5 and f double prime of c equals r. So this is kind of a convoluted looking problem. The key on this one is the fact that they said there's a c on some interval and we have a derivative being guaranteed to equal some number. We just need to find out what that number is. So if you think about this for a while, what is f double prime the derivative of? Oh, it's the derivative of f prime. So what we're basically saying here is that we want to find an r value such that the derivative of f prime equals that over the interval from 0 to 0.5. If we're talking about the derivative of something being guaranteed to equal a number, we're talking about the mean value theorem. So since f prime is differentiable on 0 to 0.5, and we know this is differentiable on 0 to 0.5 because f double prime, they said, was positive on that interval. So if it's positive, it has to exist. Since we're differentiable for the function in question, f prime, that means that we can use the mean value theorem to figure out what this r value has to be. So using the mean value theorem, what this means is that there's an x value of c somewhere between 0 and 0.5 where the IROC of f prime and the average rate of change of f prime over 0 to 0.5 are going to be the same thing. So we need to figure out what the average rate of change of f prime is over the interval from 0 to 0.5. Then we can see what it needs to match when we do f double prime of some c value. So average rate of change of f prime, that's going to be f prime of 0.5 minus f prime of 0 over 0.5 minus 0. So that's going to be 3 minus 0 over 0.5, which if you want, you could simplify to 6. So we've actually almost answered the question, but we haven't quite answered it yet, because they said find a positive real number r, and we haven't done that yet. I mean, we found it, but we haven't actually come out and said that, hey, this is r right here. So we're going to write a little bit more about that. I'm going to write, just to wrap this thing up, If r equals 6, then the MVT guarantees that f double prime of 6, the slope of f prime, is going to be 6 somewhere between 0 and 0.5.